Oh, hi, Mike.
Hi. I'm in the breakout room. I see. Okay.
If you're ready to break out, break out.
Is that your personal private library in the background, Scott?
A small fraction of it, yes.
Yes.
Okay.
I see that yours is there as well. And John, I don't know what it is about us, we freaks that collect books.
This is a small part of my upstairs. This is a science bit. I've got downstairs and then in the basement. I've got all over the place. So I just can't resist. The trouble is, I just can't resist buying books, but I don't have time to read most of them. So.
Yeah.
I don't know what you're talking about.
I have no idea. No.
The cool thing I have is that behind these shelves is a daybed and then more bookshelves. And so I can take an afternoon nap surrounded by books.
Yeah.
And that is one of the most relaxing things in my life.
And you get to absorb all the knowledge through osmosis.
Yeah, or I can just reach up and grab one and actually read it.
All right, Dave says we're going live in 1 minute. I might call Abby again, see if she remembers.
Yeah, I was asked how many books we had in our house. So I went around and actually counted them. And I got over 6,000 books in our house. And, a lot of them are paperbacks, but that's still, that counts. That's a book.
Right. Yeah.
He's doing the Abby call. And I don't know when we're actually supposed to be on.
Probably, yeah. Soon. Hello, Abby. Okay, great. That's all I needed.
Evidently, Abby is in the process of logging in.
Yep.
Now, as I said, I did get a message from Ivan that he would not be with us this weekend, that he had other plans going, and said, congratulations, go to it. And Mike, we're with you all the way.
Mushy, mushy.
Mushy, mushy?
Yeah.
That's like mashed potatoes, isn't it?
It's the Japanese equivalent of hello.
Yeah.
It's how you answer the phone in Japan.
Ni hao is in Chinese. Ni hao, right? So hello in Chinese. I know that my housemate is learning Chinese.
Alexander Graham Bell apparently used ahoy.
Yes. Which I guess is great because, of course, he's up in Boston, which, what the heck? Yeah.
All right, we're live now.
Oh, we're live.
So don't say anything inappropriate.
Oh.
Let's see. I don't know. I can't imagine anything inappropriate, much less say anything inappropriate.
You've shut us all up.
Oh, yeah.
Yeah.
Everybody was having fun talking about their library books and how to say hello in different languages. Welcome to Sidewalk Science. Abby will be joining us here in a moment. Our other regular speaker or participant, Dr. Ivan Phillips, will not be able to join us today. But we're switching things up this week. After our last program, when we did a moderately deep dive into Bayes' theorem and rationality and whatnot, what we've decided is that going forward, until we decide to change again, we're going to have kind of a thematic approach to our programs, and each one of us panelists in turn will choose a topic, and that topic hopefully will be the center of much of the conversation for that particular program. Last time we met, it was Ivan and rationality and Bayes' theorem. This week it's
And
going.
what are the odds against that?
It is. It's really.
Hi, Abby.
Hi, Abby. This week we're going to be talking about the idea of fortuitous settings for some of the levers and knobs and dials that dictate the properties of the universe. And Mike Albrow, a physicist from CERN and Fermilab, has given a hour or hour and a half lecture about this previously. And Mike, I think you call it miracles or miracles in nature, something like that.
Well, miracles, something like that. Yeah. I don't know. Obviously, I won't talk a long time. I just pick out some of the topics that I talked about on my long lecture, which was a Theosophical Society, actually. So I did that in October.
Okay.
So some topics that I don't know if you want me to dive into that, or we have other things to chat about first.
Yeah. First.
News.
Yeah. First, we'll do a little bit of science news. And
Yeah.
then after a few minutes of that, we'll delve into some examples of the remarkably fortuitous settings for some of the parameters that dictate the behavior of the universe from a physical standpoint. Before we get started, I need to tell you all that we are supported in part by a grant from the American Humanist Association. And many of us here on the panel are members of a local chapter based out of Naperville near Chicago called the Prairie State Humanists. And it is our goal to talk about the intersection of science and a prosperous and well-informed life, as well as issues around secularism and humanism that might be relevant to science. So without further ado, as it were, thank you all for joining us. You can see the URL pasted into the video chat. If you go to that site, you can join into the Zoom conference, but you will go through a moderator first, just to make sure that we don't get any inappropriate teenagers wanting to join a call and talk about inappropriate things. But we're speaking of appropriate things. Let's talk about some science news.
Yep. 3 things on Mars.
3 things
In
on Mars.
1 week, we got 3 things on Mars.
That's
Well,
amazing.
around or at.
Including a helicopter.
Including a hectoflopper. And so we have the world's first nuclear-powered aircraft on another planet.
Has it actually flown?
I don't believe not yet.
Yeah, I think it's supposed to be like 30 days or something.
I don't think it's flown yet. Yeah, so yeah, it's a little helicopter. They call it helicopter. It's really a drone in a sense because it's not got anybody in it. But yeah, that's exciting. Because the atmosphere is only 1% of the Earth's atmosphere, so that makes it very hard for a helicopter. But the gravity is a bit less, which helps a bit. So
Well, I'm just thinking about the size of the propeller and the mass of this object. It's really something if they can get it off the ground and then get it back to where it's supposed to be. That's very exciting.
I wonder if they tested it on Mount Everest, on the top of Mount Everest, or someplace with.
They did test it in the stratosphere.
Yeah, did they really? Wow. That's
Cool.
awesome.
why would they do that? They just test it in a big tank.
Yeah, put it in a big tank and suck the air out.
You don't need to take it up to the stratosphere to do that.
Tell us more, John.
I don't really remember. I remember reading about the tests a couple of years ago, but I don't remember the details.
Okay.
See, absolutely no reason for testing it in the stratosphere. You just
No.
a big tank and pump it out to 1% of atmospheric pressure and then let it fly. And if it flies on
Well,
Earth,
You go,
In a tank, you can't practice maneuvers.
Hmm.
In the stratosphere, you can fly it around and see how fast you can go sideways and things like that.
We've done that in our car.
yes.
I know.
Mm.
Yeah.
Mhm.
But it isn't to get to the Martian level doesn't take a terribly fancy balloon.
Okay.
Back in my much younger days, I used to do astronomy from scientific balloons that flew to 0.1% of the Earth's atmospheric density. And those were challenging. 1% isn't that hard.
Yeah. Wow. Let's see. You said you had three. Oh, there are 3 rovers on
And
Mars.
then
well, not on because the UAR one isn't landed.
There's a
It's in
satellite.
orbit. It's in orbit, yeah.
Okay.
And the Chinese one is a lander.
It's not
Okay.
landed yet. It's looking for a place to land. It's going to. It plans to.
Mhm.
The
Is
only
it-
one that landed is Perseverance,
Yeah, it's just
And-
still looking.
and it has moved. It's moved about 5 meters or something as of yesterday. So it's working.
And our cat has joined us. Oh, what would science be without a basic cat? Yes.
Nice. Abby, do you have any I know that we've frequently talked about vaccination program and COVID. I don't know if you want to give any updates on anything you've learned about that, or
I haven't learned much of anything new this week, so I'll give it a pass unless somebody has a question or says, but what about?
yeah, there was like a couple of variants that are being
Yeah.
tested.
Yeah, the Brazilian one is just coming around.
Yeah, a Brazilian one, a New York one, a UK one, and whatnot. And most of those I hear are still able to be combated by the vaccine and the antibodies that your body produces in response to the vaccine. But the Brazilian one, I guess, is causing a little more concern. One of the things we've heard is that this might turn, I think, Abby, you've said this, is that this may turn into kind of an annual get this year's COVID vaccine.
Get your flu shot, get your COVID shot.
These things evolve in the wild. The microbes, the lifespan of a microbe is so small, and a virus is so small, so short, that it can undergo substantial Darwinian and natural selection and evolution on timescales that are even a year or less.
Let's see, in dinosaur news, they've got what is supposed to be the world's largest, I'm going to say Brontosaurus diplodocus type animal down in Argentina again. And so this, once again, whatever size limits we thought we had, wrong. There's another bigger one sitting out there someplace, and we're just waiting for it.
I mean, I remember seeing fossils for, I guess it was like literally called Gigantosaurus. And that's astounding all by.
I'm trying to remember the name of it, and it's up here, but it's not here.
Maybe it's super duper Gigantosaurus or something like that.
No, it's actually an odd name, and I'm trying to remember what it is, but it's, again, it's a big critter.
Yeah.
On the other end of the size scale, I was reading about a lizard they found that is fits on your fingertip. It's about.
Oh yeah, I saw that.
Tiny thing. Yeah.
That's amazing.
It's the smallest reptile they found ever.
Wow.
It's thumbnail size.
Yeah. And that's
Literally.
full grown.
I knew that there were tiny frogs. I'd never heard of a tiny lizard before.
Yeah.
That's amazing.
A cat would have a grand time.
How small can it go? Abby, how small can a living thing be?
Well, I mean, I think what you're really asking is how small can a multicellular thing be, or how small can a vertebrate be? Because, I mean, you can have single-celled organisms that are only one cell big, and even cells have different sizes. And then you can have small things like in the plant world, things like bryophytes that just don't get that big. And in fact, they're multicellular, but they can never get that big because they don't have tubes. And anytime you get a tube in biology, then you can transport things around in a body, and you're no longer dependent upon sort of direct, immediate outside to inside diffusion to get some of the things you need. But if what you're asking is about vertebrates, sort of animals with skeletons like ours and the usual arrangement of organs and this kind of thing, that's a different matter. And I'm kind of astounded at the idea of a reptile that tiny, but it's
amazing.
Kind of amazing.
Yeah.
Well, the thing is that the infant must be much smaller because it has to be big. The egg has to be smaller than the
thing that
lays it, and then
the eggs.
Right, that's what. Yeah.
The eggs are going to be just dots.
Well, human eggs are pretty bloody small too, actually. So we started.
The shells on the outside and all that stuff.
Yeah.
Shell on the outside of ours. But it is true, you can get a lot of cell division before you actually get expansion.
Okay. Yeah, it was kind of an open-ended question, and I'm delighted where you went with it, and this idea of a vertebrate with all the typical sort of vertebrate organs.
Oh yeah,
squished into a size of a fingernail.
You look at it, and it's a perfectly normal lizard. It could be a monitor lizard, except it's really small.
All right. So I think that's pretty much all the time we want to take for science news this week. Let's start the second part of our program, which is more theme oriented.
Miracles, you hear me okay, right?
Yeah, we can hear you fine.
Okay, so why, I'm a scientist. Why am I talking about miracles? What do I mean by miracles and what don't I mean? So one thing I don't mean is walking on water and turning water into wine, at least for real. I mean, you might appear to do that if you're a good magician, but what I mean by miracles, you can look in a dictionary and see what they say about miracles. And obviously, usually they have a couple of definitions. One, the Oxford Dictionary says, for example, one definition is simply a remarkable event or development that brings very welcome consequences. Well, I would say the Big Bang is such a thing. It's a remarkable thing. It has welcome consequences. The other definition in parallel is an extraordinary and welcome event that is not explicable by natural or scientific laws. And I'm going to go with that, but I'll give you my wrinkle on it. It continues actually and is therefore attributed to a divine agency. Now, that's what many people would think, but I don't know what a divine agency is, so I'm ignoring the second part of that definition. So what I mean by miracle in this talk is something amazing that, while not violating established laws of physics, didn't have to be true, is known to be true, and allows us to be here as living conscious beings, okay? So it doesn't violate laws of physics as we know them, but it didn't have to be true either. But we happen to be here. So I do include things like the masses of particles, the forces between them, and so on, the size of the universe, the age of the universe, and stuff like that. And I'm going to give a couple of main examples. Can I share slides? Is that possible? Will people see them if I share my screen?
You can use, if they enable screen sharing, then you can.
Yeah, I need to check in with Dave because we're using a secondary program to get from Zoom to the internet. And so
I see a slide.
well,
Oh, there's a slide. Yes. Okay.
You can see them, but can the people see them, Dave?
I don't know. I'm trying to check in with Dave and he's not responding. The man upstairs who's controlling the technology. Let me, Mike, before you move on, give me just a, or you can continue talking, but I'll go.
No, I won't continue. I'll wait because I can do it without the slides, but it helps if I have them. That's all.
Yeah, I'll just go make sure that they're on the broadcast and that Dave's got that covered, and I'll be right back.
All right, I'll just hang on.
Hey guys, hold on just a second. Wait, hold on just a second.
Yeah, he's got to make an adjustment on the computer.
The man upstairs is making an adjustment.
You know, sometimes you just let things roll like they are and all chaos will break loose. So you got to make an adjustment. And we're talking about miracles anyway.
And that's our thing, is chaos.
Yeah.
So I'm looking at this cool slide. I got a neutron.
Well, nobody can see it yet.
And it's got a W.
Yeah,
And that's a map. And it's electron and anti-neutrino.
hang on just a second.
Wow. I mean, cool. But people can hear, right?
Okay, you
Okay.
are good to go.
We got the slide up. All right, go ahead,
Okay.
Mike.
Okay, very good. So here's one thing which I think is sort of pretty amazing, which is that neutrons are slightly heavier than protons, and they decay to protons if left alone. If they're stuck in a nucleus, they don't have to, but if they're left alone, they decay with an average life of about 15 minutes. So, you know, within an hour or two after the Big Bang, the neutrons have decayed. Now, the reason they can decay to a proton is because they're slightly heavier. The difference is very small. It's about 0.1%. I'd put the masses there in units of MeV. Doesn't matter what the units are, but you see a neutron's mass is 939.565, proton 938.727. So 272, the difference 1.293 MeV, which is just over the mass of the electron and a neutrino. So the neutron is able to decay to a proton, electron, and neutrinos, and that's what they do if they're left alone. Now, why is it heavier than the proton? They're very similar particles, but if you look inside them, at the bottom you see a diagram showing at the deeper level of quarks. On the left you see a neutron which has got 2 down quarks and 1 up quark, and the proton's got 2 up quarks and 1 down quark. Now what happens is the down quark has got a mass of 4.7 MeV. It's much less than the proton mass. The proton and neutron masses are mostly due to the internal motion of the quarks and the gluons and so on. But the down quark is slightly heavier than the up quark, but only by a little. And it's a bit surprising to me because the electric charge of the up quark is twice that of the down quark. So you might think it would naturally be heavier, but it's not. And nobody knows why it's that way around. If it was the other way around, then the protons would all have decayed into neutrons, and then you couldn't have hydrogen. After the Big Bang, you'd have a hot plasma of neutrons and electrons and positrons and neutrinos, but no hydrogen atoms. So that is a rather remarkable thing. Fine tuning, as Scott said, the dials turned that way. Now, theoretically, we think that these up and down quarks get their mass by coupling with the Higgs boson, but that doesn't answer the question of why that's that way around. We don't have a theory to calculate the masses from first principles.
So Mike, can I interrupt you with questions, or do you want to wait for questions until?
No, you can interrupt, yes.
Okay. Sure. So there's no, I'm just clarifying for people in our audience as well as myself. So there's no physical rule, no equation of physics, no law of nature that specifies why the up and down quark should be different at all, much less why one should be heavier than the other, or by how much one should be heavier than the other. These are all things that are completely unspecified by every theory we have. Is that correct?
That's correct as of this moment. Now, there are actually not just these two quarks, there are 4 other quarks that are all unstable and decay, the strange and charm and top and bottom quarks. So there's 6 total quarks, and they all got different masses. And we don't have a theory that tells you what masses, the masses they have. Now, so that's 6 parameters, if you like, that are put there. And maybe there is an underlying theory we haven't got yet that will be able to predict the ratios of these masses or the masses themselves, but we haven't got there yet. So, the quarks get their mass by coupling with this so-called Higgs field, which likes to couple to the heaviest things. So the top quark, which has got a mass of about 175,000 MeV. It's very, very heavy. Okay, it's about as heavy as a gold nucleus, but that couples strongly to the Higgs field. We have no theory that will predict these masses, or the masses of the other 6 quarks that we've got. They're just measured. Okay.
Yeah. Is the same thing true for an electron? Is there any way to predict the mass of an electron?
It's also true for the electron. Now, the electron has got 2 heavy partners, the muon and the tau. They've got their high masses, but nobody knows how to calculate those masses, and so we don't have a theory for their masses. Having said so, that there are 3 types of neutrino that go along with these 3 electron-like particles. There's electron, the muon, which is about 200 times heavier than the electron, and then there's a tau. They've each got their neutrinos that go with them. We don't have a theory for the mass of the neutrinos either. So if you count the electrons and the neutrinos, there's actually 12 fundamental particles, all with different masses, and we do not have a theory for them for their masses. But on this particular one, it's particularly, I mean, the others, the others are all unstable and decay, but the neutron and proton, they've been around for a long time. But so, okay, so that's one thing. Another thing, which is even more fine-tuned, if you like, starts to come on the next slide. So this is the existence of carbon. So carbon is a particularly special element because it's the only one that seems to allow complex molecules to build up, really complex ones like RNA, DNA, and so on. And where did it come from? Because when the universe started with the Big Bang, which was of course not big, it was much smaller than the proton, we think, but in the first seconds or minutes of expansion, we had neutrons and protons. Neutrons hadn't yet decayed, and they could make, and you could get deuterium by a neutron and proton being stuck together. A neutron could stick to that and make tritium nucleus, which could decay by radiating a gamma ray. And then a proton could stick to it and make helium-4. But while this is going on, the universe is expanding very, very fast. And these nuclei are all running away from each other. And a little bit of lithium with 3 protons was made, but nothing heavier than that, because the universe seemed to be expanding so fast. So there was no carbon or nitrogen or oxygen or any of these heavier elements made at the Big Bang. They had to be made in stars that were formed much later and cooked. And so the neutrons would decay. Their mean life, as I said, about 15 minutes. So, you have, if you like, a few hours after the Big Bang, you've got a plasma of protons and electrons and neutrinos and a little bit of helium and lithium, but not much else. And then after about 380,000 years, ABB, that's an acronym for after the Big Bang, as distinct from AD, the universe is cool enough for atoms to form. Electrons and protons formed hydrogen atoms, and the universe then became transparent and light could stream through. So that's when you see the microwave background, you're looking at the light that was filling the universe at about 380,000 years. So where did the carbon come from? Without carbon. So there could have been no life before carbon. I would state that, and we'll see a bit on the next slide here. It's unique among the elements. It's got 4 links to hydrogen. So you can easily form methane, methanol, ethane, all these helium molecules. Now, of all the elements, there's another tetravalent element called silicon and germanium too, to some extent, but they don't make these big complex things. They make it, you can have silane, which is like a sort of pulsive smelling toxic gas. It's like methane, but with silicon instead. So silicon makes polymers, but there are no rich complex molecules like RNA, DNA, which seem to be necessary for life made of based on silicon.
Mike, can I interrupt my question? So is it my preconception from probably something I've read years ago is that silicon binds other atoms so tightly that it's hard to break silicon bonds compared to carbon bonds and carbon hydrogen bonds. So it takes lower energy, and it can be compatible with the energy of hot water and other things to enable the solution, a solvent solution of organic molecules with carbon, whereas silicon, because it binds other atoms more tightly, is less able to be gregarious in chemical reactions. Is that, you're a chemist too? Does that sound right? Yeah.
Silicon really likes to bind to oxygen.
Yes.
Make silicon.
Oxygen. Absolutely.
And it doesn't, in the lab and in a chemical factory, you can talk it into making other sorts of bonds, but in nature, it makes rocks.
Yeah, and silicon carbide also. So again, it makes rocks.
Okay.
Whereas carbon bonds to itself. And it goes on and on. Oh, it's beautiful. Yay,
Yeah.
carbon.
So Mike, what you're saying is that carbon is a miraculous element.
Yeah, on the next slide of the periodic table. Before I get there, I would just say, what about silicon-based life? People talk about it. Well, maybe, silicon-based life in the form of robots will take over the Earth and we will be their pets or something like that. So, but silicon-based life cannot, I believe, occur naturally for these various reasons. And here on the next slide, you see the periodic table of the elements. I've ringed carbon there. It's element 6 and hydrogen, those two. Which the hydrogen, as I said, is a miracle because it happens to be the proton's lighter than the neutron. And the carbon is a miracle. How did that get there? And there's a miraculous fine-tuning thing that enabled carbon to exist prolifically enough to form light. Now, of all these elements, if carbon was deleted from this table, I think the universe would be sterile. Okay.
Yes, I would agree.
Now, on the next slide, see, I'm saying it's the only element with just the right atomic structure to allow such a vast variety of complex molecules. You see this one, it's a tiny section of DNA. It's not just carbon. You've got nitrogen, oxygen, and phosphorus there as well, forming these things. And that's much too complicated. I'm a particle physicist, so I like simple things. Anyway, that's the same. Now,
the carbon is the backbone. everything else hangs off the carbon.
Yeah, it's essential. I mean, yeah. So I can't judge whether things like phosphorus are also essential, but they had to be formed as well. But way back, Fred Hoyle, who was a brilliant English astrophysicist, cosmologist, and one of my favorite science fiction authors. Actually, I loved these books when I was a kid.
Black Cloud is behind me. Among
You've
those-
got a copy too.
Yeah, and A for Andromeda, brilliant. That was a novel of that was how a civilization from a far distant exoplanet somewhere else in the universe was able to invade Earth by sending a radio message, which we picked up, and it was a coded message for how to build a computer, how to program it, and what the data to put in it, and it convinced us to make life. Anyway, now, so he was a great science fiction author. But he believed in the steady state universe. He didn't believe in the Big Bang. He coined that term, actually. He invented the term as a derogatory term, Big Bang rubbish, He said, he believed in the perfect cosmological principle by which the universe on a big scale is the same, not only everywhere in space, but everywhere in time as well. So it had to be, anyway, people don't believe him about that anymore, but he was, there's a thing called the Hoyle resonance. So back in 1953, he said, how can the universe possibly have so much carbon? How could it be made in stars? So in this little diagram on the left, you see a process by which carbon can be formed in stars. Two helium nuclei can stick together to form beryllium-8, emitting a gamma ray to get rid of some energy. And then a third helium can join the beryllium to form carbon-12. Now, unfortunately, beryllium is very unstable and it decays in almost no time at all, okay? 10 to the minus 17 seconds. So how could this possibly happen?
This particular beryllium, Mike, or all beryllium is unstable?
This is beryllium-8, beryllium-8. I mean, there's different, there's...
the natural isotope that we make metal out of is beryllium-9.
And it's more stable?
Oh, yes.
It's stable, period.
This is highly unstable. But you can't make beryllium-9 by combining two helium nuclei, you see. You've only got helium nuclei in the soup. So you've got to make them, you can't make beryllium-9, you make beryllium-8, but it's got to grab a helium before it actually decays to form carbon. And Hoyle said this can only happen if there's an excited state of the carbon nucleus, the carbon-12 nucleus, with an internal energy, he said, 7.68 MeV energy that enables the carbon nucleus to be formed, okay, by technically the cross section of helium and beryllium-8 is big. And he calculated that energy, and he then told Willie Fowler, who was at Caltech, that there should be an excited state of the carbon-12 nucleus with an energy of about 7.68 MeV. And the calculation, of course, is detailed balance between the strong nuclear force and the electrostatic repulsion of the protons in the nucleus. But he said the energy of excited carbon state must be between 7.3 and 7.9 MeV to produce enough carbon for life to exist, and a bit bigger range just to have the abundance of carbon observed. And Fowler and his student, I think, or postdoc, did the measurements and found that stayed exactly at 7.656 MeV. So this excited state of that nucleus, which means that internal energy, okay, is between around the 7 MeV to enable that process to happen. And also, that's not the only thing. The oxygen nucleus also has to have just the right energy level. Otherwise, there'd be much more oxygen than carbon would be made. And carbon's only produced actually in very hot and exploding stars. So, but this is sort of, it's amazing to me because the properties of this, the carbon nucleus has to be just right. All this nuclear physics has to be just right.
Mike, you said that there was, when he was doing his calculations, you have to take into account the strength of what we call the strong nuclear force that binds atomic nuclei together so that nuclei don't fly apart and they're all radioactive. So that's the strong nuclear force. You have to balance that with the repulsive energy of the protons pushing against each other inside the nucleus. And am I interpreting this correctly, that that balance between the pulling together of the strong nuclear force and the pushing apart of the electromagnetic force, that balance is resting on a knife edge to be able to allow carbon to be formed from that beryllium absorbing a helium? The forces have to be just almost perfectly balanced for that.
That's right. That's right. Yes, that's right. And of course, I mean, Hoyle didn't have a theory for the strong force between protons and neutrons at that stage, but there were measurements of these nuclear energy levels and so on and so forth. So, yeah, it's just, you're right about that. So,
Is there an energy well type of situation here that exists that would naturally have everything sort of falling into that particular energy? Or is it just, wow, it just happened and it shouldn't have?
Carbon is more stable than helium. It is of lower energy. It has lower energy than 3 helium nuclei. On the other hand, the miracle is that there's a pathway to get you from the helium nuclei to the carbon that actually is likely, because that amount of energy is not very large, and without this special pathway, you couldn't make carbon out of helium with any sort of yield.
So you got sort of one of these curves that it starts up and it goes through the beryllium state and then drops down and ends up at essentially a lower energy state than either of the previous plateaus. And so you have an extremely stable atom there that's going to hang around for 13.82 billion years.
Carbon 12 is, as far as we know, perfectly stable.
Yeah, it just sits there.
And so at a deep level, it's related again to these relative strengths between electromagnetism and the strong force, which, as Mike said, Hoyle didn't know about any details of the strong force. He knew there had to be something binding the nucleons together, and that there had to be this little gap in energies, the resonance in energy, where it was able to essentially form this carbon from adding a helium to a beryllium.
Yeah, I mean, if beryllium 8 did not exist, you might think you could make carbon 12 by combining 3 heliums together all at once, but the chance of 3 coming together all at once is so small that this is the way to do it, as he writes. And it's the fact that he was able to calculate the energy of this excited state, and it came out just right. And by the way, on the bottom right, you see a graph of basically the probability of carbon being produced as a function of temperature, because the energy has to be right. Oh, okay, this is the Cno cycle in the stars I put there, which this is energy production in the stars and the sun. The Cno, so there's an energy production in stars heavier than the sun, which uses carbon, nitrogen, oxygen as catalysts in the cycle. In the sun, that process is only a small fraction of the energy production in the sun. But just recently, actually, a collaboration called Cno says they have detected neutrinos from the Cno cycle to show that it actually is there. But normally, the sun comes from helium and deuterium fusion. Anyway, that's a by the way. So I think this is one of the most remarkable things, actually, the way how carbon could be produced. And of course, that's one of many things. Okay, my next slide about Goldilocks.
A star has to run out of hydrogen. And then what happens is that it contracts, and the contraction makes the core of the star hotter. And that's what gets the temperature up to the point where the triple alpha process can happen.
And the density as well, right? Presumably.
That's right. Yep.
Yeah. So, well, I've got another couple of slides about planet Goldilocks principle of planets. This is sort of taken from that thing. So it's a bit of there are the miracles. The Earth is not too hot, not too cold, but just right for life. And since from ancient times until 1781, we just knew about Mercury, Venus, Mars, Jupiter, and Saturn, and the Earth, and then Uranus, Neptune, Pluto were discovered. Now we have discovered over 4,000 exoplanets, planets around other stars. And but most of the ones we've discovered happen to be close enough to their star and massive enough that we could detect the star wobbling and so on. But now Kepler, this is an artist's impression of a planet that could be cool enough, warm enough to have liquid water. It's one of the Kepler 186f. Anyway, so now is there life everywhere? So with so many, so we now are finding planets, exoplanets around nearly all the stars where we can detect them. So with 100,000 million stars in our galaxy, roughly, there's probably something like 100,000 million planets, give or take, in our galaxy. And even if only 1% had life, that's still a billion planets, or let's say capable of having life. I'm not saying have life yet. So as I said, the carbon atom is the only one of the elements. Now, you've probably all heard of this Drake equation. Frank Drake was trying to make some estimate or guesstimate of how many planets there might be that had life or even civilizations that we could maybe emitting radio waves that we could detect by listening to radio signals, SETI. So he put down a list of seven things that one would like to sort of try and estimate, to multiply together to estimate the number of planets or civilizations, if you like, in our galaxy. And we didn't know, we now know the first three of these. The average rate of star formation in our galaxy, we now know pretty well. And the fraction of those that have planets, we now know is not far off 1. The average number of planets that can potentially support life for a star that has planets. And we don't know that very precisely, but even if it's 1%, that still is a vast number of planets, as I said, like a billion in our galaxy. But we don't have any real knowledge of the last 4 here. The fraction of planets that could support life that actually do develop life at some point, we don't know. The fraction of planets with life that actually go on to develop intelligent life or civilizations. The fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and the length of time for which such civilizations release detectable. All these numbers are to do with the probability that we could actually detect a radio signal from another planet. Now, we are getting to know some of these, like the fraction of planets that could actually support life, but we don't know if they did. But I think a key question is the bottom one. How long does a civilization like ours survive? We know that it's, we don't know anything about the last 4 of it, except they're not exactly 0 because we are here. But if civilizations like ours only survive for a few thousand years, then that's a very small fraction of the time of the universe. So the next slide, sort of what do I think? We can discuss this, but what do I think about life elsewhere? We once thought the Earth was unique, that this was the world, and that was, God made the world, and that was it, and the stars were in the heaven and so on. But then along came science and physics and telescopes and satellites and gravity wobbles by spectra and so on. Now we know that our planet is one of thousands of discovered planets around other suns. It's extremely likely, in my opinion, that some form of life has originated on at least millions of planets. And we may know in our lifetimes, your lifetimes if you're younger, because we have ways of detecting signs of life on other planets around other stars. But then, what are the chances of multicellular life then evolving to sentient creatures? Life on Earth, I think, it was something like a billion years before actually multicellular life started, and then evolution sort of took off. But then what are the chances that something like a civilization arrives and survives a while with conscious beings like birds or whales? So I just put down a number here. 13.7 billion years is about the age of the universe. If you take 13,700 years as something like a civilization, that's 10 to the minus 6. Okay. If you talk about how long we've been able to emit radio, then it's it's 1% of that. All we know is it's not zero, so we could be alone. But there are 100 billion galaxies in the visible universe. So, and there may be 10 to the vast number of universes, question mark. And that's really my next slide is, and the last one, because I've put a lot of words on here. I'm sorry about that, but I just touched on two of the miracles, the hydrogen and carbon, that seem to be very fine-tuned, probably the only element allowing life, and not made in the Big Bang, but a delicate interplay of forces. And that I didn't mention other miracles like the age of the universe and the expansion rate. It didn't happen too fast, didn't happen too slow, but just right. I mean, if the universe had collapsed in before the first stars had formed, then it wouldn't be life. If it expanded too fast, then that would be a different story as well. Matter antimatter difference. There seems to be there is a tiny difference between matter and antimatter, and it seems that allowed matter to dominate, and the antimatter that we think at the very Big Bang was equal to matter, nearly all annihilated, allowing the remnant matter to dominate. And we know that our universe is dominantly matter. And then the galaxies and stars and non-uniformities in the universe, we think arose from quantum fluctuations, which brings in, Planck's constant in the very beginning of the Big Bang, giving rise to these things. And if you change Planck's constant, you're going to change the structure of the universe because it was amplified by the expansion. Neutron, heavier than proton, I said that. Neutrinos also exist, and if they didn't, and they're weakly interacting, so they come out from the center of sun and stars and allow them to be stable. And there's a lot of other established physics that I say that's science, and all these things, if they were changed dramatically or even not dramatically, then life could not exist. Now, in my humble opinion, what do I believe about that? Because, if there's only one universe, there's no way all these things are just pure chance. But on the other hand, a designer with a capital D makes no sense either to me, because a designer must be complex also. So you get into this regression. How did the designer require carbon life as well? Anyway, but fundamental physics has got a finite number of parameters. They're masses and particles, they're 12, as I said now, forces and strengths, speed of light, things like that. I don't know how many fundamental parameters there are. At the moment, the list is like 24. But if we find a theory that relates all the particle masses, that number could come down to 16 or whatever, 8, whatever it is. It doesn't really matter. But those parameters, you can think of them as a point on an n-dimensional graph. So 24-dimensional graph or 8-dimensional graph, whatever. One point is the phase space. Now, if there are a vast number of distinct universes, each with different parameters, so each universe is a different random point in this n-dimensional phase space, then if you have enough, then you're going to get some that are just right for life. Now, if they're 10 to the 80, I just said just a big number, 80 decimal places, right? I don't think there's infinite, but 10 to the 80 is not infinite. Then if 10 to the 79 are sterile, that is still about 10 to the 80 allowing life, because take 10 to the 79 and from 10 to the 80 and you get 9 times 10 to the 79, it's about 10 to the 80. So these are just big numbers anyway. So this is the multiverse idea that we have, and after all, we've gone up in the number of worlds, a number of stars, a number of galaxies. Hubble said there's many galaxies out there. So this is what I in my opinion, that we have a vast number of universes, but it's not quite science until it can be disproved. And then if you ask, how did those 10 to the 80 universes come into existence? I just say, don't ask, don't tell. So that's my final word on that. So I think there's plenty of food for discussion there.
So thank you, Mike. That's a great overview of some of the fortuitous circumstances. Now, I note that you were careful to use a definition of miracle that emphasized the fortuitous and surprising nature of some qualities of nature. And you explicitly left off the implication of some kind of design or designer. I appreciate that largely because of your clarification you made of if it was designed, whether by an alien species that creates universes or by what we might, whatever God means, whatever some people might mean when they say God, we still have to ask the questions, as you noted, in the infinite regress of where did those alien beings that create universes, where did they come from? Did they come from some other universe? Did they create a universe machine like, much more complicated than CERN or the LHC? The questions never stop. So maybe it's easier just to stop at saying the universe has properties inherently that allow for various parameters that define physical reality. And that leads to the idea of fairly directly of the multiverse. If this is one of an infinite variety of ways the universe could exist, and it happens obviously to be amenable to living things, then all of, or very many of the other ways that a universe could exist might not lead to living beings. And that is a plausibility argument, going back to what we were talking about last week with Bayes' theorem. We can talk about plausible science, even if it's not something we can directly measure, because it's an extrapolation of what we do know already. And that's what Bayes' logic bids us do, is to take into account things we already know. So the multiverse is a plausible extrapolation of some of the characteristics of the universe that we know about, including the early Big Bang and the inflationary epoch and whatnot. So at no point in there is it necessary from a scientific standpoint to say a miracle occurred. We can say it's just a property of our universe, or it's a property of sort of a motherverse. That's what I call it sometimes, a motherverse or a metaverse that is capable of birthing new universes with different parameters endlessly.
Yeah, there are many different pictures of of multiverse ideas. One is that if you go 20 billion light years away, then the parameters of physics change. That's not my view. My view is that actually I think of our universe as being like a vacuum fluctuation in an outer space time, which could be finite and closed in space and outer time, but that there is a vast number of these disconnected bubble universes, if you like. They have to be disconnected because they may have different numbers of dimensions of space. It could some have 2 or 3 or 4 or 5 dimensions of space. I don't know, but even if they all have 3 dimensions of space and 1 of time, then they have to have different parameters. Now, I do accept that we may well, and I do hope that we come to a theory which enables us to calculate the masses of these 12 different fermion particles, but so that would reduce the number of free parameters we have. Other people say, no, there's just 12 different numbers, and you could change any of them and the universe would still, you'd have a different universe, but it would still
be, logically consistent.
Yeah, right.
There's another miracle, Abby. I wanted to make sure that you have a role to play in this discussion as well. It's not all about physics. There's also the using miracle in the non-supernatural term. There's also the miracle of eukaryotic life, the complex cells with a nucleus that enable multicellular life to arise. As Mike alluded to, the planet Earth went along for something like 2 or 3 billion years before eukaryotes emerged from primitive bacteria precursors. And maybe that was a 1 in a quintillion or more chance. Maybe it was such an unlikely event that we're very fortuitous to live on a planet where it happened. Do you have more thoughts about that?
Well, there are a bunch of things in evolution that really are sort of, turning points. One is certainly when you get eukaryotic cells, which are bigger and more complex than bacteria and cyanobacteria and things like that. So that is a really important one. And bacteria are capable of forming colonies, films, things like that. So, but they never really get into true multicellularity. That's what eukaryotes do. You were quite right about that. Eukaryotes are all things that have cells like ours, but it includes single-celled organisms, like amoebas and stuff like that. There are a couple of other things that wind up being important. I already mentioned tubes as sort of crucial to multicellularity. And there's also, I remember one where somebody did a computer simulation where they found out that segmentation of bodies is another one of those stages that then enables a great multiplication of life forms. So, there's eukaryotic cells, there's tubes, there's segmentation, and segmentation maybe even came before tubes, I'm not sure. But all of those things are necessary in order to have organisms that are as complex as us or my cat here. Who's wanting to show up.
Speaking of complex organisms.
Complex organisms, right. So, there's a bunch of things like that without which we would not have, technological species. And that actually reminded me of another thing maybe it was like 2 slides ago, Michael, where you had evolution of complex life and evolution of intelligence. Somewhere there was something about intelligence in there.
Was that in this one?
I don't know. Maybe the next one, I think.
Multicellular life.
I say, what are the chances of multicellular life and evolving?
Multicellular life, then evolving into sentient creatures. There's a step there that I think is missing. And this may have to do with your definition of sentient, but then there is sentient creatures developing technology.
Yeah.
Because we're now finding that there are a lot of animals that are a lot smarter than we were giving them credit for.
Yeah.
There was the recent article about, I think it was cuttlefish that passed the marshmallow test.
Yeah.
Of being able to sort of resist immediate reward for a greater future reward, which is a pretty complex thought process, and it involves the idea of a future. So they're smarter than we were giving them credit for. We obviously have things like chimpanzees and apes. We have dolphins that are really smart. It turns out that some birds, the corvids, crows and jays, and also various different parrot-like birds are really, really smart. But none of them developed technology.
Yeah.
And I think there may even be a difference between intelligence and the ability to develop technology, because that requires both brains and a way to manipulate the world, i.e.
Yeah, like dolphins are very intelligent, but they don't have technology, right?
And they couldn't light fires to smelt iron under the ocean.
Yeah.
Right. They couldn't hold a hammer and make something. They couldn't even invent a hammer. I mean, they do use tools a little bit, but you don't. And obviously we know about various different animals that use tools and even make simple tools, but we haven't really seen that leap into technology. So I think that's kind of an important step as well.
Right, sure,
Well,
yeah.
doesn't that involve this?
That's what I was getting at. There's these things here that really make a difference.
Yeah, and so we coordinate this with these to do things like this.
Right.
where Other creatures don't have that, this
The
and
dexterity.
this. They have one or the other.
we can manipulate our environments to a far greater degree than other organisms can, because we've got hands. We've got something that can grab, and a lot of fuss is made over the opposable thumb. And in some ways it really is just a slight variation in quality, because, kangaroos have hands. If you've ever looked at them, they're pretty remarkable. But once you get, the thumb doing this, it enables both a fine grip like this, but also a power grip for gripping hammers. And that turns out to be pretty important. And so it may have even been something as dumb as that enabled technology.
The other comment I'd make is that SETI has long been looking for radio signals, and that reflects kind of a 20th century perspective. The way we're using radio is actually getting less detectable over interstellar distances with time, because the most detectable signals are carrier waves and other framing things, which, with our crude radio technology, consume a lot of power but have very low entropy. And that's what makes them detectable over long distances. But as we improve our technology, radio gets more and more like random noise, unless
it's old hat, isn't it? Right. So, yeah. And by the way, even if there's a million planets in our galaxy that have developed technology, the nearest one is likely to be 1,000 light years away. The galaxy is rather big, so it's not
just that it's old hat. It's that the characteristics of radio are getting more and more like natural noise.
Yeah.
And you need the magic decoder ring to tell the difference between the natural noise and the technological signal, as opposed to 20th century radio, where every radio station was transmitting a big whopping carrier wave.
Right.
What you're saying is that as civilization becomes more advanced, you're going to hear less from it.
Yes.
It's only civilizations at that short span in time between developing technology and getting really good or even better at technology that they're going to be detectable at a distance by radio waves.
That's right.
Okay, fun.
That's great. We've got a comment on YouTube. Our viewer, Ray, says he's taking issue with my characterization of a plausible science. He said that's an oxymoron akin to Christian science. Well, it seems plausible to Christian scientists, but I think clearly not what we call science. So let me take just a minute and a half and clarify that. There's a huge amount of philosophical debate about, for example, the multiverse idea. In principle, like Mike was saying, if multiverses exist, in principle, they're not accessible to our universe. So we cannot measure them, we cannot experiment on them, etc. So one of the reasons that scientists take the idea of a multiverse seriously, some scientists, other scientists, I will admit, say that it's not a scientific concept and we shouldn't be talking about it. But some scientists take it seriously because it does entail a plausible extrapolation of things we know to be true. So that's where the plausibility comes in. It's not plausible just because a scientist says it, or it's not plausible just because somebody wants it to be true. It's plausible because it follows from a causal chain of reasoning based upon things that we've previously verified. And that's how Bayesian sort of reasoning works too, that we talked about last week. But Ray, you're absolutely right there, at least with regard to the fact that many scientists and philosophers think the whole idea of a multiverse is beyond the realm of even scientific speculation, that it's a non-scientific thing.
Okay.
There's also that group that looking at the microwave background, and there's a doohickey, if you will, an inconsistency as we look at the microwave background. And several people have said, well, that's where the interaction actually occurred that was the position that the Big Bang occurred.
Nonsense. Okay, I think it's not.
And-
As Scott said,
And you
in
go,
principle, the
hello.
universes are disconnected from us. And I was careful in my last slide to distinguish between science and my humble opinion, right? But I'm a scientist, and I can say yes, the multiverse it's outside the realm of science, but I can be a philosopher too, right? I don't have to only think science and not think anything else. So this is what I believe. It's my faith, if you like.
As long as we label it properly.
Yeah.
Scott, I have a special request from a member of the audience here that he be allowed to join us. He's sitting right next to me, and he works at Sky and Telescope magazine and wishes to interject. Can he join us?
I hope so. You can try going to the URL that or you can just talk.
Hi.
Oh, well, you don't even have to join that
Hi,
way.
Alan.
Talk to us.
Hi.
Hi, Alan.
He's desperate to get into this conversation here, so take it away.
Are you just joining, or have you been with us all the time? Did you hear what I had to say, or are you just joining now?
He's been listening and is desperate to get involved here, so.
I've briefly been a senior editor of Sky and Telescope for many, many years. I've been the cosmology guy there and the SETI guy there for some decades, semi-retired now. But before we dismiss the idea of a multiverse as outside of science and untestable and uncheckable, the history of science is that what seems impossible to one generation of scientists becomes available to another one. And also the motivation for the whole idea of a multiverse comes from physics. We know that how the Big Bang happened, the inflationary scenario, which seems unavoidable because many aspects of the universe and the process of the Big Bang are inexplicable any other way, predicts that there will be not just one Big Bang, but an enormous number of them. Ours is just one of them. And once this process gets started in a larger outer realm, it basically is unstoppable, and you get a fantastically large number of universes spawning off indefinitely. The more we learn about cosmology, the more we're discovering how the Big Bang worked, the more inescapable inflation seems to be. So there is solid physical rationale for that idea. What we don't know is, in these other universes, will the laws of physics be the same as here, or will they be different enough to allow all different kinds of universes, including the extremely rare ones where we have just all of the perfect alignments and flukes of chance that make any organized matter in life possible. On the other hand, if you've got something like string theory, which has something like 10 to the 500th power possible solutions by some people's calculations, different universes could embody any one of those, depending how string theory happens to collapse in the first moments. And there you've got all the range of physical properties that you could imagine. So there is more than philosophy going on here. Philosophy is what science can't do yet. And science has a way of making fools of philosophers by, as time goes on, actually answering their unanswerable questions.
Yeah,
Thank you, Jack. Can I comment? Thanks for that. I agree pretty well. I'm glad you said an enormous number and not an infinite number, because I have an actual thing against infinity, but 10 to the 100 is as far from infinity as 2 is. But the other comment I have was that if all these other universes had the same physical properties as ours, it does not solve the issue of how come, they have to all have different, not necessarily different dimensions, but different physics,
Yeah.
different physics.
Yeah, so there are many different motivations for the idea of a multiverse. There's the quantum multiverse. There's the multiverse that's entailed in the idea that the Big Bang created much more matter than we can see in our cosmic horizon. So there very likely is additional universe generated during the Big Bang that lays beyond what we will ever be able to see. But that part of the manifold of the multiple universes would have the same physical laws as the part that we do see. On the other hand, like Alan was saying, there's an argument for a multiverse based upon different inflationary epochs. One of the miracles that Mike, you did not mention, but I'm sure you're aware of, is nobody has any idea what would cause the inflationary epoch of the universe to shut off. And that's one of the ideas that led Alan Guth and some others to come up with the notion. I think Andre Linde is another, come up with the idea of eternal inflation, is that maybe when inflationary epoch, maybe when it stops is completely random. And so there's the inflationary multiverse. There's probably 6 or 8 kinds of multiverse, and we don't really have knowledge about which ones are more or less plausible.
Yeah, we have enough problems figuring out our own.
Yeah.
Never mind one which is, to us, imaginary.
Another obvious thing that I didn't, well, there are many that I didn't mention, but another one is the value of the Higgs field, or we call it the vacuum excitation value of the Higgs field.
Yeah.
So the Higgs, the idea that the electron, for example, gets its mass by interacting with the Higgs field. If the value of that was changed, the electron mass would change. And if it switched off, the electron would become massless, and there'd be no atom because the electron would zip off at the speed of light. But yeah, so actually, Alan is your name, right? So yeah, are you still with the Sky and Telescope, or are you disconnected from it now?
I'm semi-retired. I'm doing 1 day a week of work there, but still following these things as best I can.
Okay. So yeah, I'm retired 4 years since from Fermilab now, but still working every day on there. And actually, I'm thinking of writing this lecture about miracles up and submitting it to some journal. I think maybe
Or even a popular book, Mike. You might try your hand at.
Well, I'm doing that. That's another project. That's
Oh, good.
We all have these projects.
Well,
Yeah.
John and Joanne, neither of you has spoken a lot during this conversation. Do you
I've been listening.
do you have other examples you can think of amazing circumstances?
Well, my lecture is going to be the next one. That's going to be in 2 weeks. And I'm going to be asking the interesting question, is the universe left-handed? Again, coming back to these same principles that we've been talking about. And of course, this is all based on carbon. And without carbon, there is no, as far as, in my discussion of chemistry of left-handedness. And so it's going to be an interesting discussion on that point of view of chemistry. The physics has already occurred. Now we have atoms. Now that we have carbon, all the other questions are solved. We have carbon.
Yeah.
Actually, I'm going to ask the chemist there about water. It strikes me as that's another one of those kind of miracle substances. When it solidifies, it gets lighter. It gets less dense. It floats, which is kind of amazing.
Lava doesn't do that.
And almost nothing else floats when it solidifies.
Water and antimony.
But we don't care about antimony. But yeah, you're right. I mean, that is amazing about ice, isn't it?
And it releases heat very slowly. It gains heat very slowly, which actually is part of the reason why we can be warm-blooded. It's not just that we make a lot of heat, but that we retain it because we're mostly made out of water. Water has a lot of properties that enable life.
Think of the surface tension of water.
Right.
There's the surface tension. There's the fact that it's a good polar solvent. There's just lots of things about water that are kind of special.
It's the new miracle drug.
Right.
I want to patent it.
Looking for life. What's the first thing that gives us a clue there might be life on a planet? Water.
Water.
Yeah.
Water is not made of carbon, but we can't really live without it.
Right.
And the surface tension enabled Mosquito Jesus to walk on water, right?
Yeah. Yep.
Let me throw in my 2 cents about a miracle which involves water, and that is that we talk about habitable zone planets and all that, but the habitable zone shifts as a star ages. Stars get more luminous as they get older, and somehow the Earth has remained hospitable for life for something approaching 4 billion years. And that actually seems fairly remarkable. It's sufficiently remarkable that there's something called the Gaia hypothesis that life regulates the temperature of the planet. I'm not sure I believe that, but if that is what happened, that in itself is a miracle. So I don't know. Is the Earth just the example of the pencil that stood on its sharp end for 4 billion years? Because it's not possible.
Go ahead, Alan.
So do you think that Mars was once had flowing water and nice clouds and blue skies and creatures roaming around? We may find out one about that. But
the answer to that is, well, you think it's so unlikely that a pencil would balance to one part in the quadrillion perfection that it would stand on its point for a while. Well, we have no way of saying that the Earth was not so super fantastically lucky to maintain a habitable climate for 4 billion years, because we wouldn't be on a world that wasn't.
Right.
So unusual that it happens just once in some tiny far corner of the entire universe. We will find ourselves right there observing that phenomenon because we're it.
We wouldn't want to ask the question.
This is called the Anthropic Principle. The idea that our present requires certain things to have happened in order that we can be here. And that's an example of this that's nice and simple that I use is, aren't you lucky that you were born on the planet Earth where there is air to breathe and water to drink, and in our Unitarian hymnal there is an old New England hymn saying how God has provided everything we need. Why weren't you born on the moon? You would have died. How awful that would have been. You would have strangled in vacuum in the first 15 seconds of your life. Aren't you lucky? Even
would not have liked it.
Like the moon, worlds like the moon.
Alan, the probability
rarer than the Earth.
The probability that the 6 of us human beings are here in this conversation is so 10 to the minus 50, whatever it is. I mean, it's unbelievable. So therefore, it's impossible that we're here. We're just not here.
Well, Alan mentioned the moon too. The moon itself is a highly unlikely thing that has been fortuitous in the history of Earth.
Most propitious.
Yeah, it could have given rise to the thin crust that allows for plate tectonics and the recycling of elements. The moon might have been implicated in some of the strong early tides on Earth that might have created some tidal pools.
And stabilizing our rotation.
Right, where life originated. I mean, so, we can continue finding these fortuitous events. But like Alan said, if these events weren't fortuitous, we wouldn't be here to talk about it. So it's not magical, but it is very fortuitous.
And again, as Mike pointed out, if there are 10 to the 50th universes, one of them must have something like ours. Mm-hmm. And again, I also ask silly questions like, is it random that these numbers come up and we go, aha, or is it a function of the object itself? Is it almost preordained that an electron will be this big? And, as it comes out of this ether, whatever we want to call it, that initially begins this universe as a nothing, does the precipitation occur because, well, like salt or salt water, whatever is the beginning of it, it must precipitate out in this way because that's its constituents.
Yeah, I think nobody knows yet. There could be other physical laws that say if you've got an energetic vacuum state, a primordial vacuum state, that it can only decay in certain ways. And those ways lead to protons, neutrons, electrons, top and
And if that proto state is this big, it's going to do one thing. And if
Yeah.
it's this big, it's going to do another thing. And if it's this big, it's going to do a third thing, and so forth. So it's the precondition
right.
to the universe that decides whether or not we have electrons or protons and that kind of thing. But once it's started, it's going to happen. It will happen.
Yeah, that much is true, because obviously we see it
Well,
around.
But I mean, you can imagine among these 10 to the 80 or 10 to the 100 or whatever universes, there's one that has the electron, just very similar, but the electron happens to be half the mass or twice the mass, and that everything changes. But anyway, just think of a point in this 24-dimensional space, or whatever it is, a parameter space, and scatter points all over that space, and it'd be and see what fraction of them could give rise to complexity. Anyway.
Yeah, some people have done some studies on those parameters. There's a book. I'm sorry, I can't remember the title of it. There's a huge tome. I mean, it's a big, heavy, thick book about the Anthropic Principle and some of the parameter space that allows our universe to exist. And I think some of the scientists involved in writing that book examined this. How much different could the freezing point of water be? How much different could some of the nuclear processes that happen in stars, how much different could those be? How much different could the electromagnetic force be compared to the strong force? And there is some wiggle room in many of these parameters, especially if they happen in lockstep. But there's not
much wiggle room. That's what I've been saying. Not much wiggle room, but some people think 10 to the 80 is not much different from 10 to the 79, but actually it's a big difference.
It's 10 times bigger.
The big difference, we kind of understand the wiggle room in the parameters as they are, but what we don't understand is whether there are other places in the parameter space where complexity can arise.
Indeed.
Yeah.
Indeed.
Say that just because what we're not interested in is how precisely we can produce our own world with human beings. It's how can we produce a universe that will produce any complex matter where self-organization can take place by a flow of energy through it.
Right.
And that may be, there may be many, many other varieties of combinations of physical constants and laws that allow that. And heck, astronomers, astrobiologists can't even answer what's the probability of the formation of life with our own known laws of physics, much less other laws of physics.
Right.
Yep. Anyway, it's all very mind-stretching and mind-boggling and so on. Another thing that just comes to mind is, as I said, there's 3 pairs of quarks. There's the up and down that we know and love that make us. There's a charm and strange, and there's a top and bottom that were discovered at Fermilab. Now, what role do the top and bottom quarks have? Well, theoretically, that third family was predicted because we know that the weak interaction is handed. It's called CP violation. It allows matter to be different from antimatter. And these theories said that if there wasn't a third family of quarks and leptons, then we wouldn't be able to have this CP violation. In other words, it may be that this top and bottom quark existence, even though they're very unstable, allows matter to dominate over antimatter. I mean, these are all things that are all tied up. I mean, so
yeah.
Yeah.
It's amazing how little we actually know.
On the other hand, it's amazing how much we do know.
Yeah.
Just little monkeys on a little dust ball around one star out of 100 billion in our galaxy.
And every time we think we know something, we explore it, and then 10 more questions arise. You go, wow.
Yeah.
As the frontiers of knowledge expand, the boundary expands too. So what you don't know is more and more.
Yeah.
Yeah. Yeah. In the closing couple minutes, if you'll allow me, I want to return to this idea of a designer and the sort of classical idea of a miracle, which is magic and some magician that did it. And I understand the motivation whenever we come to a gap in science, whether it's the supposed fine tuning of the universe, or whether it's an explanation for human consciousness. You know, there's a tendency to say, we don't understand this. We don't understand how it could be this way, how it could have come about. So
Therefore,
there must literally be magic. And, you know, science has a history of killing magicians right and left, even if we call them gods, right? So I think the track record of science is pretty well established. That's one point. And then the second point is back to the point you made originally, Mike, that if there are such magicians, what rules govern them? What rules govern what's possible, where they come from, how they're able to process information? You know, that's a thermodynamic process.
where did they come from?
Well,
Right.
yeah, so James-
Or God's all the way up. When I was 10 years old, it occurred to me, wait a minute, if God created everything, who made God?
exactly, that's the regression. Yeah.
God is saying there's a bigger God, higher up and more powerful than our God, and he made our God. So
Not all the way up, right?
one,
Not all the way up.
Yeah.
God's all the way up.
So about, you know, when I gave this talk at the Theosophical Society, I advertised a book called The Sins of Jesus by Richard Muller, who's a physicist actually. And it's a historical novel about the life of Jesus. And it's a very, I love that book actually. I had him to dinner and he gave me a copy of the book. But in this story, you see how Jesus performed his miracles by actually magic tricks. Okay, he's a magician. Magicians can do crazy stuff, right? You don't believe, how can they do it?
Like Penn and Teller magician, right? Not Gandalf magician.
No,
Oh.
I mean, James Randi magician. You know, James Randi, a great magician. Like he'd do magic tricks. Brilliant. He said they're tricks. You know,
Jesus's contemporary Heron of Alexandria made his living creating magic tricks for cults.
Yeah.
They're good
So
at it.
in the story, I mean, spoiler alert. So Jesus had this, you know, he'd gone up, he'd learned healing, he'd learned magic and so on. And he came back with his message of universal love. Love everybody. Don't just love your friends, love your enemy too. And he was preaching this on his soapbox and nobody was listening to him, you see. They're just walking away. Lots of prophets in those days in Israel. And then at a party, they ran out of wine. And then some wine reappeared. They found some in the basement or something. People thought he turned water into wine. And by thinking that, they listened to him. My gosh, he must be the word of God, you know. So then he figured out that he could get his message of universal love across by performing magic tricks like walking on water and stuff.
Getting people to pay attention.
It's a great story. I recommend it if you can get it for a few bucks. The Sins of Jesus by Richard Muller.
I'll look for it. Sounds like fun.
Yeah.
Well, we've reached our hour-and-a-half limit for
Already?
this
Oh my,
this week. We'll be back in 2 weeks. Joanne, you're going to lead a discussion
I'm gonna lead it.
about the left-handed universe.
Is the universe left-handed?
And you know, we're available. You can leave comments on YouTube even after the broadcast, and maybe we'll get to them next week. And in any case, thank you all for joining us. Alan, it was really a pleasure to
Great
have
see
you
Alan.
as a participant. And thanks to
Have you.
everyone else.
And your cat is more than welcome.
Right.
You know it.
Take care, everybody.
Bye.
Bye, everybody.